Okay, so I remind you what we did last time. We considered an atom inside the external magnetic field, and the first magnetic, the first field that we considered, so that was DC field, so I mean a bias field or constant field. We considered magnetic field, and we started to consider electric field, and we considered this DC Stark effect. And we understood that there is a difference between the application of magnetic field and electric field. The essence of difference is that the magnetic field acts on angular momenta degrees of freedom, spins, and angular momentum of the electron. So the part of the wave function that was involved in these calculations in order to understand what's going on was essentially the spin part of the Hamiltonian. And electric field, when it is applied on an atom, acts on the spatial degrees of freedom of the wave function, so it really distorts the wave function itself. That's essential difference between these two actors. So we studied every regime of the magnetic field, at least it's on a certain level. So part of this study you will complete starting today in the homework. And the electric field, we started to understand what's going on with the DC Stark effect. The first thing that we understood is that because the electric field is talking to spatial degrees of freedom, we have to consider parity of the wave function. So the parity of the wave function of the ground state is odd. The operator is even. The operator of the electric field. So the dipole operator, right? So it's the direction, some distance of the dipole multiplied by the electric field. So this gives us an even operator. So therefore, we have to take the integral, which is the multiplication of odd and even functions. That gives you automatically 0. This means that the ground state do not have first order Stark effect. That was the conclusion, immediate conclusion from the symmetry. It does not mean that there is no second order effect. This is what we will see here, of course, because I remind you that our calculations are perturbative calculations, so we use the perturbation theory. So the first order is 0, though we have to go to the second order. So, but before going to second order, we actually considered the DC Stark effect on the excited state. So there we saw that there is a first order effect, and this first order effect actually caused the splitting of energy levels and mixture of these energy levels. So we considered specific case of a first excited state with a principal quantum number n equal to 2, where we have the degeneracy of 4. And this degeneracy, so I remind you that we consider this situation forgetting about fine structure splitting and hyperfine structure splitting, so which sort of coming back to simple structure, which includes only Coulomb interactions. In this story, at the end, we understood that we can remove the degeneracy of, partially remove the degeneracy of these 4 levels. So 2 levels remain degenerate, but 2 other levels actually mix, and they split. And in this mixed energy levels, so if you consider the Hamiltonian of the electric field, this Hamiltonian do not commute with L square operator, so L is not a good quantum number anymore, which is essentially quite clear from some classical considerations. So we really distort the wave function. So instead of getting the wave function which is have a symmetry, we make a certain sausage in one direction. specific direction of the electric field. So this causes some distortion of spherical symmetry, and we lose the L as a good quantum number, but the M L remains a good quantum number because it's just a projection on certain axis. So this is if we choose this quantization axis as the axis which collinear with the electric field, the projection of an angular operator on this axis will be good, will stay the same, and it's indeed the good quantum number in this situation. So that's everything. Is just a short reminder of what we did a week ago. So now what we are trying to do is to complete this picture of electric dipole operator, or electric field effect on atom, by calculating the second order Stark effect on the ground state. Okay, so we just want to understand how the ground state will be affected by the electric field. So the problem here is that essentially it's possible to do exactly. So it's a second order perturbation theory. So the second order perturbation theory is a infinite sum of contributions. It's so in order to calculate the correction to the energy level, which is the energy level of 1, 0, 0, this is the background level with the principal quantum number 1, and it has 0, 0 for L and M. So we want to calculate the shift of this energy level due to the presence of the electric field. And we have to go to the second order perturbation theory. So the second order perturbation theory says that we have to take the E square, which is the E0 is the amplitude of the electric field, and we have to multiply by the sum over all wave functions with n non-equal to 1. So it should be all energy levels except the ground state, and then all L and all M. So in here we have to close our operator, which is the Z direction, with all functions N, L, M. I don't have to put comma here. N, L, M on Z operator, and close with the ground state, which we want to calculate, square that, and it should be divided by the difference between the energy of the ground state minus the energy of end state. That's a prescription of the second order perturbation theory, right? So that's what we have to do. So this is sort of a hard part, right? Because we have to make this infinite sum, because we have infinite number of energy levels. So that's sort of a hard part. We will not do that exactly. So we will make a certain consideration. So we will make a calculation to limit this effect from above. But just for your knowledge, it's possible to calculate that exactly. But for that, you have to be smart. So you have to find some operator that commute, some smart and nice operator that commute with the Hamiltonian, which is not a trivial operator. And if you find some nice operator that commute with the Hamiltonian, so you have to find this energy levels of this operator. It is possible to do that exactly. So I'm not doing that. I'm doing a different approach. So we will actually estimate this value from above. So in order to be able to calculate this sum in an easier manner. So in order to do that, we have to. So we have to deal with this part. So we essentially take this value, right, and ask ourselves what's going on with this difference if I am changing a principal quantum number, n. So if this n runs from 2 to infinity. So in any case, once we have the difference, right, it's always, once the n is larger than 1 or equal to 1, it will be always negative. So this means that actually this effect should shift up the energy level. So instead of having the energy level, for example, of hydrogen atom to be equal to minus 13.6 electron volt, it will be shifted a bit up. So what we can do, we can replace all these n numbers. So instead of dividing by E1 minus E2 minus E3 and so on and so forth, we will replace that by the difference between the between the ground state and the first excited state. And therefore, we could actually take this difference and shift and move it outside of sum. So this means that it will be not equal, but it will be less than E squared, E0 squared divided by the E1 minus E2 multiplied by sum that goes from n not equal to 1 Lm to infinity, and this one will be equal to, so this sum goes over the wave function that closing the z operator and ground state here. So this part I didn't touch yet. So but this part I sort of simplified. So I took out the large difference, and I know that this is not correct because I have to run over all principal quantum numbers, but I know that in any case this will be the largest value, so everything, so this shift should be less than what I calculate here, right? So that's the idea. So, and I know that why I'm doing that, so because E1 minus E2 is essentially the largest difference, right? It goes, the energy goes like a 1 over n squared. So this is the largest gap, and all others give me less contribution. So I think that this, I can imagine that this contribution would be the most significant contribution to the story. Okay, now how to calculate that? So this is essentially something that we can trick here. So this is the multiplication, right? So let me write it outside. So this gives me the following. So this sum over n L m z 100 squared give me the sum over multiplication of that. So 100 z n l m up, and I'm closing that with n l m z 100, right? So now I'm paying attention that n l m sum over this element is essentially 1, because we have a complete basis of this eigenstate, and therefore I can actually exchange this sum as a 100 matrix element which closes z square operator. 100 closes the z square operator between the ground state wave function. So this is essentially what we need to calculate. This is not very complex things to calculate, because this is essentially boils down to calculate the R square expectation value, which we already did. So I did that in advance with all expectation values of all different R operators when we studied hydrogen atom. And now we can just write down the answer. So Z square operator, the expectation value of the Z square operator is equal to 1/3 of the expectation value of R square operator. Okay? And we can say that this is essentially equal to A squared Bohr radius divided by Z squared. Okay, so now we know what we have from this sum. Therefore, we can say that this is equal to the 8/3, 8 divided by 3 multiplied by 4 pi epsilon 0 multiplied by A 0 to the 3rd power divided by Z to the 4th power multiplied by, so I'm of course taking into account what is the difference between E1, E2, right? So this gives me the additional 8 Bohr radius and the additional Z square. Now this is multiplied by E0 squared. So essentially it's done, right? So this calculation is done, so we know what does this gives us. So this means that we expect to have this delta E 100 to be smaller. So let's take it as a modulus. We know that it shifts up the energy. So it should be smaller than this guy. I will put it here in order to have it close. Z to the 4th and epsilon 0 squared. Now, what we know from this story, so there is a definition of a certain value which we call polarizability of an atom. So the definition of the polarizability of the atom is it goes like so this the induced dipole that we produce by applying the electric field on the atom should be equal to minus the gradient of the change in energy as due to the second order perturbation theory, right? We can put here 2 just to remind ourselves that this is second order perturbation theory divided by dz, d epsilon 0. How strong the field, right? So that's the definition of this induced dipole moment. That's the induced dipole moment. Induced dipole moment. So and this induced dipole moment is equal to a certain polarizability that we call alpha multiplied by the field. So it means that the induced dipole moment depends on the field. So if that's the meaning of the induced dipole moment. So the interaction with the atom due to the presence of the electric field goes in 2 steps, sort of. Because the atom is neutral, right? So electric field cannot walk directly on the electron or the proton, so it's a neutron object. So now the first step in this interaction is that the electric field induced dipole makes the dipole, it destroys the atom, and then the second step is this electric field acts upon this induced dipole. That's why it goes in the epsilon square, so in the strength of the field in the second power and not the linear. But if we introduce the induced dipole D, which is equal to alpha multiplied by epsilon 0, then we sort of can say that this is multiplied by so this induced dipole multiplied by E0 gives us a regular type of interaction between the dipole and the electric field. So anyway, the only thing that I need from this story is just this derivative. So this derivative actually gives me a factor of 1/2, right? Because I'm taking the derivative of that guy. It gives me a factor of 2. So a factor of 2 that drops down. And this factor of 2 gives me an additional factor of 2 or additional factor of 1/2, depending on what you exactly define. So I can say that this delta E of the second order perturbation is actually equal to 1/2 minus 1/2 induced dipole multiplied by E0 squared. So now we can from here actually say what is this induced dipole. So this induced dipole, therefore, is less than this part multiplied by 2. So it's a 16 divided by 3 multiplied by 4 pi epsilon 0 multiplied by A0 to the third power divided by Z to the fourth power. So that can be calculated. So everything is known here, right? Up to Z, which is the atom number. So this guy is equal essentially in atomic units. This is especially simple because everything is 1. So in atomic units, it will be just 5.33 divided by Z, the atomic number to the fourth power. So this essentially 5.33 is 16 divided by 3 multiplied by 1. Right. So now it's this is essentially the value in atomic units, right? I emphasize here that this is in atomic units. This alpha is equal to sort of, should be less than 5.33 divided by Z to the fourth power. Right, yeah. It's 16 divided by 3, check me. That's equal to 5.33. Yeah, what?
No, yeah, but this number, not the second one.
That one?
Yeah.
Well, this is that one. Exactly, right? So it's just this one multiplied by 2. That's just that. Okay. So and now the exact number actually is not that far from here. So I remind you that we estimated from above this number. So this number should be less. So it's indeed less. So the exact number that this polarizability is equal to actually 4.5 divided by Z to the fourth power. That exact number. Exact calculations. So we are not that far, right? So this simple estimation of the value gives us the value which is not very far from the precise. Well, it's still tens of % of mistake, which is not tolerable in this course, of course. But this calculation costs about 5 minutes, so the precise calculation costs you much more, and you will get this number once you do this calculation. So this is the value of this polarizability of an atom. So you can see that this value goes with Z number in a very strong power, right? So remember that this is a ground state. So you can imagine why Z here in so strong power. I remind you that this is the distortion of the ground state of the electron. Once we increase the Z, and this is the wave function is the wave function of hydrogen. So we have to consider here some sort of hydrogenic system with one electron which is coupled to a nuclei, to the nucleus, and this now has Z equal to 1, right, for hydrogen. So this, then the polarizability is equal to 4.5 in the atomic units. But if we increase Z, so we add another proton, so the electron will be much stronger bound. And this, because of this binding for the proton, distortion of the external electric field of the system will be much less than with a single proton, because the wave function is of course shrink down, right? It shrinks as a Z squared, so it shrinks very strong. So, and to apply, we'll have to apply much stronger electric field in order to get to the same polarizability. So it sort of makes sense that Z should be in this position and should be in strong power. Okay? Right, so now let's think about the situation of very strong electric field. So that was sort of perturbation theory. So this perturbation theory works well when the electric field is relatively small, so relatively weak. What does it mean? Relatively weak as compared to what? As compared to of course, the Coulomb interaction between the electron and the proton, right? So if we consider electric field which is weak, then everything is okay. But if we start to apply electric field of the order of the interaction strengths between the proton and the electron, that should change the essence of the atom, right? So we actually start to question the existence of an atom. And this is, of course, cannot work due to the perturbation theory. So this is the last part of our consideration of DC Stark effect. So we want to ask ourselves what's going on with the strong electric field. So that's the limit of strong electric field. So strong electric field. Electric field limit. So what's going on here? Right, so in this case, so in atomic units, one unit of the electric field, will be equal to charge of the electron divided by 4 pi epsilon 0 multiplied by the Bohr radius squared. So this will give me some value, which is 5.14 10 to the 9 volt divided by centimeter squared, divided by centimeter. So that's the value unit of the electric field in atomic units, right? 1 unit in atomic units. So this is essentially the characteristic electric field that describe or characterize the strengths of attraction between the electron and the proton. When once the electron sits on the ground state orbital. So this is why the Bohr radius is here in this story. So this is sort of a unit of electric field in atomic units. So in order to, this is the question of how strong the electric field should be, right, in order to distort the Coulomb interaction between the atom and the electron. So this is of the order of the electric field that we have to do, right? So is that latch or not? So let's check that in a moment. So we can imagine, right, how this distortion will work. So if we consider a certain axis, suppose Z axis, that's the axis collinear with the direction of the electric field. So now this is the energy. So in this axis, right, the Coulomb potential goes like a 1 over R. And it goes also for negative part. So here in the center we have the proton. Now this is the how the electric field or electric, and so it's Coulomb interaction goes like a 1 over R. So now on that we have to put the electric field, the interaction between the electric field and the electron. And so this interaction is linear, so it goes like right, this interaction equal to E multiplied by E0 multiplied by Z. Right, so it's 0 here, and it goes linear with some coefficient. Positive to the positive Z, negative to the positive to the negative Z. So that's this part of the interaction with the external electric field, and that's the Coulomb potential. So now the sum of these two stories, of course, will give me some sort of disturbed potential of this shape, right? So this potential will be stronger here. And it will produce some point here of the maximum of the potential, and then this potential will be disturbed and goes to a negative potential. That's the sum of these two potentials, so the Coulomb potential and the interaction with external electric field. So this means that we have a saddle point here, right? So this is the saddle point. Through this saddle point, the electron can escape, essentially, right? So if the electric field, the external electric field, is strong enough, so we can actually ionize the atom, right? So this, the question is where this saddle point is, and what is the strength of this saddle point? Essentially, where this saddle point is, ZD. That's the question. And the second question is, what is the strength of this potential at this point? So that is simple mathematical questions that we can easily answer. So we know that this potential, V of Z, which is the sum of these two potentials in this story, it's the minus 1 over 4 times pi epsilon 0 multiplied by E squared divided by Z. And now, so that's the modulus Z. So this is not, okay, that's the coordinate now. This is the potential, right? So this is not the atom number, that's the coordinate. Oh, this describes the Coulomb potential, 1 over R, that we are looking only at Z direction. And now there is a second part, plus epsilon, so plus the charge of the electron multiplied by the epsilon 0 multiplied by Z, right? So again, the coordinate, so that's the potential. So now we can, so this minus is just because we consider this story at the negative Z part, right? So we know that the saddle point that we are looking at exists at negative position of the coordinate. So now we are looking at the, so essentially we need to take the derivative of this as respect to Z. So derivative will give us right? So we have to keep here the negative sign. So E squared divided by Z squared. And then we have the part which has only E epsilon 0. So this has to be 0, right, of course. And we're from that getting the ZD, which is the modulus. Or this is, we know that this is negative. So in modulus, it will be just the square root of the 1 over 4 times pi epsilon 0 multiplied by the charge of the electron divided by epsilon 0. Sorry, epsilon 0, yeah, E0. So this is epsilon 0, this is E0, right? The strength of the electric field. Okay, now this is essentially the position. And now we can calculate the potential at this position. So B potential at Z equal to ZD at the saddle point. This potential will be equal to minus 1 over 4 times pi epsilon 0 multiplied by charge of the electron squared multiplied by all these guys, ZD to the power of minus 1. And the second part is minus E epsilon 0 multiplied by ZD. So substituting this ZD into this story, we are getting, therefore, the V potential at Z equal to ZD. The saddle point will be equal to minus 2 multiplied by 1 over 4 pi epsilon 0 multiplied by E squared multiplied by E0 into the power of 1/2. So that's the potential at the saddle point. Well, if this saddle point will reach this a certain bound state, this bound state will stop to be bound, right? Well, because you have, this is the energy, right? So in this energy, if I'm not considering the Z direction, I've just considered the bound state. So at this position, there's, let's say that this is the ground state of the atom, right? So here, this is the first excited, this is second excited, so on and so forth. And there are many energy levels, infinite number of energy levels, that goes up to a continuum. So this saddle point, actually say, where is the line above which all these energy levels becomes unbound. Okay, because this is essentially brings you to continuum, right? So above this saddle point, the electron can escape to infinity. It can go because the energy of the electron is larger than the potential. So the potential is not now this guy. So where was this potential, all the energy, all the bound states are bound, truly bound, and there are infinite number of them up to continuum. But here, because of the distortion, not all of them remains bound. And this saddle point actually says, this potential says where this line above which all the energy levels becomes unbound. At certain point, right, once, this depends on the strength of the electric field. Once, at certain point, right, we can say that we can ask ourselves at which value of this potential the bound state, the ground state of the hydrogen atom becomes unbound. So which means that no atom exists in the world. Hydrogen atom, we are destroying the hydrogen atom, that's the real bomb, right? So no more atoms in the world. So for that you have to apply certain electric field, right? So, and this essentially more or less the question of how it goes, right? So, and this is what we are trying to answer. So, how it goes? It goes in this manner. So, according to this formula, we can say that minus 2 square root of epsilon, the E0, square root of E0, will be equal, right? So in atomic units, forget about that. This in atomic units. So I'm jumping here from regular units to atomic units just to make sure that nobody slips, right? So if anybody fall in sleep, you will not follow. So this is the same expression as written here, but in atomic units, which means that this is equal to 1, this is equal to 1. So what is left is only here. And now I'm asking, when this becomes, equal to some energy of a certain bound state. So this is equal to 2 times 1/2 into the divided 1 divided by 2n square, right? And this is minus. So these are the energy levels in atomic units, right? It goes like a 1 over n squared, but there is a 1/2 because the energy in atomic units is 2 times the excitation energy of a hydrogen atom. So that's this is how it goes. So right, so we know that the epsilon 0 that we need to have will be equal to, it goes like this field goes like 1 over 16 multiplied by divided by n to the 4th power. That actually answers the question, what should be the field in order to be equal to a certain bound state. Right. So it goes very strong with the principal quantum number, which means that it should be very easy to reach a highly excited state of hydrogen atom, right? So it's not, we don't need to work very hard in order to unbound highly excited states. And this is indeed very easily can be done if we are doing experiments with Rydberg atoms. So I remind you that the Rydberg atom is an atom with high excited electrons. That electron sits at very highly excited principal number states. We call this Rydberg atom, and this Rydberg atom, this formula, for example, says that the Rydberg atom will be extremely sensitive to electric fields, to external electric field. It's probably not very surprising, but here is the quantitative analysis, which is not very complicated, that tells you how strong the effect is. So it goes like a 1 over n to the 4th power. So we can reach quite easily this electric field, and we can understand that the electric field will be extremely, so the Rydberg atom will be extremely sensitive. So if you go to a highly excited state, tens or 100, that will be easily disturbed by the electric field, external electric fields. So now what about the, getting this one equal to 1, so this electric field should be 1 over 16 in atomic units. So this is the electric field in atomic units, right? So this is why we have it. So in order to unbound the ground state, so in order to take the electron and ionize the atom from the ground state, the electric field that we need to do is this electric field divided by 16. So we have that 16. So it's an order of magnitude less than the electric field in atomic units. But this means that the electric field that we need will be about the 10 to the 8 volt divided by centimeter. Is that large or not? So it's large. This electric field is indeed extremely large. But this electric field can be reached if we use the intensity. So we can use the electric field. We can use a laser with intensity. Certain intensity. So what is this intensity? So this intensity should be 5 multiplied by 10 to the 14 watt per centimeter squared. So that's the intensity of the laser that can produce this electric field. For n equal to 1, right, this electric field will be at E0 equal to 1 over 16 in atomic units, and this is the field in atomic units. So we need this laser in order to ionize our atom. Is it possible or not? So I don't know if you're familiar with this, with lasers. This number is large. So these numbers are not for theoreticians, of course. Theoreticians do not know real numbers. So these numbers are only interesting for experimentalists. So among you. So the experimentalists like to know these numbers. Is it possible or not? So for those of you who is experimentalists, I can say that it is possible to do. But for that, you need the femtosecond laser. So those of you who have very short pulse of laser, you really have to go into the femtosecond regime in order to press your electric field into very short time. And if you focus it large, you can reach this number. So this means that you can get this number and you can ionize the atom from the ground state. And this is the field, so of strong electric field, and this field exists. So it's an active research field that started about 2 decades ago. And this field actually gives you the high harmonic generation. If you heard about that, some of you probably yes. So high harmonic generation field is the field of how to go from below the femtosecond regime of lasers. So there's just short few sentences about that. So if you start to think about femtosecond field, right, you will realize that femtosecond is sort of something that relates to the oscillation frequencies of the field, right? And the visual wavelengths is about 10 to the 14, 10 to the 15 per second, right? So, and this is the same order of magnitude, the length of the pulse and the oscillation of the electric field. So, which means that the femtosecond laser gives you one maximum, or probably few, 1, 2, 3 oscillations of the electric field, right, within the pulse. So the number of oscillations that the electric field does is very few times. It oscillates very few times. So it's extremely difficult to go from femtosecond regime down to attosecond regime, so below the femtosecond. So how to press your electric field even down the femtosecond. So suddenly you cannot produce the electric field, right, which has less than 1 oscillation. It sort of sounds like meaningless operation, right? You cannot do it as sort of theoretician trick, right? Let's do something which is less than femtosecond, but forget about that there is no such a field that oscillates so fast. So of course it will be needed to go to shorter wavelengths. So that's just to understand the attosecond science. So the attosecond should be only at a very deep UV regime, right, produced. So how to do that? So this is the way how to do that. Take the laser of femtoseconds laser and shoot the femtosecond laser at atoms. So the atom will be ionized in this story, right? So this ionization goes like that. So you know, you produce the electric field. So this is really in time. The electric field starts to oscillate, goes up, goes down. So now this certain, this is the maximum of the electric field here, suppose in this direction, right? At this point, the electron is removed from the atom, so it goes away because we produce enough electric field to ionize the atom from the ground state. So at this point, the electron goes away, but it feels the electric field, right? This electric field accelerates the electron in a certain direction, and then this electric field actually changes the direction. So changing the direction, the electron actually turns back into the direction of the same atom that it just goes away from that, right? And at this point, it actually returned toward the same proton that sort of found itself without the electron. And this electron collides with the proton, right, back. At a certain probability, this collision brings back the bound state of the atom. So the atom can be reconstructed by this simple operation, whoop, whoop, going away and going back. So you can actually reconstruct the atom, but usually the reconstruction, it's small cross-section, but it's not zero. This reconstruction usually brings back the atom at a very highly excited state. So this very highly excited state actually should decay back to the ground state and by releasing a lot of energy, and this energy is usually in deep UV. And it's everything that you can understand from this picture is coherent. So it goes together with the electric field. So that produces this ripped electron out of the story. And this coherent oscillations produce you coherent pulses of deep UV or X-rays. And this is how you can shrink actually. And these oscillations are shorter. So these pulses will be shorter than this pulse, original pulse of 1 femtoseconds. Usually this pulses goes down to 100 attoseconds, or hundreds of attoseconds, with a lot of harmonics. So you get very many ultra deep UV harmonics, and this is a hand waving explanation how it works. Okay, so you will hear now. So it's only simple sort of quasi-classical explanation how it works. Okay. Okay, so that's the end of the story from the point of view of electric field. And now what we want to do is to forget about the external fields. So we talked about the magnetic field, we talked about the electric field, we talked about the hydrogen atom, we talked about the construction of all the energy levels of this story. We talked about corrections, fine structure, hyperfine structure. Fine. Now let's talk about the real business. A real business is the business of multi-electron atom. So and let's start from a simple case. This simple case is the 2-electron atom, so the helium atom. And let's think what is the problem. What are the problems that we will see in this story? And we will see a lot of problems. Okay. Let me start from saying some simple words about 2-electron atom. So, if we understood that now we know that to deal with proton and electron is not a simple business, right? So I hope I persuaded you that this is not a simple business. Now, what do we expect from 2 electrons? So if before we had not a simple business, here we will have, unfortunately, something which is, we can say that this is, we cannot solve that. That's essentially the main conclusion. That's too complicated to be solved. Okay. So That's first of all correct. So it's hopeless, this case. Well, because there are too many bodies that try to interact, and you know that the problem of many-body physics is not a very simple problem. Usually unsolved, so you have to try to make some tricks, you know, in order to try to understand what's going on. And before we are jumping into hopeless situation in the unknown that we know that will bring us to nowhere, let's try to think about this situation and to try to understand what's going on. So we know that, you know, at least the nucleus we can leave alone. There are 2 protons there. That is what we know, at least, you know, in order to keep 2 electrons together. But there are also neutrons there in this story, of course. This is the helium atom, so the nucleus is more complex than what we have. But let's forget about the nucleus. It does this job. It provides the positive charge in order to keep 2 electrons inside the atom. So this means that we are going to neglect everything we know, all the complexities that we know from the hydrogen atom. So I sort of hint you that we will drop out fine structure effects, hyperfine structure effects, and all other complexities that we know exist. So it can be, of course, taken into account, but the story becomes complicated even if you consider only the Coulomb potential. So we should think about some sort of you know, simplifications of the story. So we know that even if nucleus we consider as a certain single particle, right, that has a charge plus 2, there are 2 electrons in the story, so we can immediately imagine that this is a story of 3-body, right? So it's a proton and 2 electrons. So 3-body problem is sort of a real problem. You cannot really write it as simple as 2-body problem. So there is no, you know, separable potentials in this story. So as I told you, it's hopeless. But what there was a clear assumption here that can be kept in mind. So the clear assumptions here says that the helium atom exists. This is some experimental fact, right? We know the helium atom exists. This is an important assumption to understand. Why this is so important? This is so important because you really can understand that interaction between the 2 electrons, which is a Coulomb interaction, right? And it should be a strong interaction, as strong as the interaction of electron with the proton, right? So that makes the question mark why it should be less strong than the interaction between the electrons with the proton. But we know, because we know the helium atom exists, we can assume that the interaction between 2 electrons will be weaker than the interaction of each electron with the proton. That's an important point to understand, right? Because we know that in order to keep them together, they have to interact with the proton stronger than the interaction between the 2 electrons. Otherwise, this business don't work, okay? And then what? Couple? Oh, you Cooper pair, right? So let's make a Cooper pair from 2 electrons, and then.
You say that the interaction between 2 electrons must be smaller than the interaction with the proton. Why would you say that?
Because 2 electrons repel each other. That's what I know from physics. I don't know if you know something else. You can tell us. So they really repel each other with the Coulomb interaction, and this Coulomb interaction just requires from us that they repel each other. So I don't know how to produce the force that will make them attractive. So if you know this way.
No, but this force is just negative, you know, like you have a positive force of the interaction, negative force.
Well, if I consider two electrons, right, so they have the same charge, so they have to repel each other. So, and we are really not in the, in the solid state, so we cannot trick the electrons and to produce some attractive interaction between two electrons which exist in some exotic phases, like a superconductor phase. So I agree that electrons can interact attractively with each other and form a pair, but for that we need a solid state environment, right? So we need some mediator here in the story in order to make the attraction between the two electrons. So our story is simpler. So we have a proton. We know that, we have a nucleus. In this nucleus we have two protons. They have a charge +2. And we have two electrons, which has, each one has -1 charge. So everything together is neutral. But, so I don't know how to produce the attractive interaction between the electrons. Yeah, that's, but this is exactly what I'm saying. So, no, this is exactly what I'm saying. I'm saying that the interaction between these two electrons have to be, this is the basic assumption, it has to be smaller than the interaction between each electron with the proton. Otherwise, we are in hopeless business. So we will prove that the helium atom does not exist. But we start from the assumption that the helium atom exists. This is a reasonable assumption, I think, right? So because sort of something in the world tells us that this is a reasonable assumption to start with. So therefore, starting with this assumption, therefore, logically follows from this assumption will be the assumption that the interaction between two electrons is weaker than the interaction between the electron and the proton. That's the logic of this thing. Okay, so this is simple, right? It's not something complex. So now I want to, so based on this assumption, I want to sort of try to, keep the story simple. So how to keep the story simple is to make another assumption which is much less evident than the first assumption. So the second assumption means that nothing bad happened that we add the second electron. This is a really bad assumption, which means that let's try to treat the system perturbatively. At this point you have to jump and say, how on earth, even if we know that helium atom exists, so there's no chance to think that electrons do not interact with each other, right? So there is an interaction between electrons, right? So, but let's sort of, go easy. Let's check sort of easy steps in this story. So this two electron atom requires us several steps. Let's start from the step which is completely crazy. So these steps means that two electrons do not interact. I know it's completely crazy, right? So, but this makes our life simple. Because we can immediately say what would be the bound energy of these two electrons to the nucleus, right? So this bound energy will be simply based on so this interaction energy will be simple. So we consider, sorry, not interaction energy. This will be simple to understand what is the bound energy of the system. So we know that energy, binding energy of the electron in the hydrogen atom to the proton goes like z square, right? So minus z square divided by 2 in atomic units. Remember, I keep you awake today. I'm jumping between the atomic units and the real units. So in atomic units, energy goes like, so that's the ground state of the story, n equal to 1. So then I have the minus 1/2 of z squared, right? So that's the first electron. Then there is a second electron, and the crazy assumption says that there is no interaction between them. So the second electron will be the same, right, from our point of view. So then we will be able to say that the bound energy of the ground state of this system will be just the sum of z squared divided by 2 twice, right? So this means that it's essentially, so z now is equal to 2, that we know, right? Because the charge of the proton, charge of the nucleus is equal to 2. So this means this is 4, and we have here minus 4 atomic units of energy, right, in this story. So I remind you that the atomic unit of energy is 2 times the ionization energy of hydrogen atom. So ionization energy of hydrogen atom is minus 13.6 electron volt in real units. So here this story means that we have here minus 8 times multiplied by 13.6 electron volt, and we come to the decision, to the conclusion that this is actually the minus 109 electron volt. That's the binding energy of the system, right? So that was easy, nothing crazy. So now we can actually ask ourselves, okay, so let's go and check in the experiment what is the ionization energy of the hydrogen atom. So I remind you that this is ionization energy of 2 electrons. So this is the binding energy of 2 electrons to, that's our calculation of the binding energy of 2 electrons to the proton, or to the nucleus, sorry. So this binding energy, in order to measure this binding energy, we have to repel 2 electrons out of the helium atom. So what we usually do, we actually take usually what we do, we measure the ionization energy of a single electron. So how much energy do we need to reply to an atom in order to remove a single electron out of the atom? So what is this binding energy in this situation? So binding energy in this situation is essentially, so the binding energy of a single electron to this story. So the binding energy of the single electron is essentially minus 54, right? The half of that, 54.5. Well, it's about 4. That's the binding energy of a single electron to the atom. So now this binding, so then in order to ionize, singly ionize, to remove a single electron out of helium atom, we will have to introduce, according to this model, we have to put 54.4 electron volts. That would be the energy needed in order to ionize, to remove a single electron out of the helium atom. So now we know experimentally that this is not true. So this is the experiment. Our guiding sort of, line in this story is sort of experimental value. So this experimental value says us, what was the experimental value? The true value, just a second. Something about. Well, 24, let me check. 24, Okay, right, that's right. So 24.6. So experiment value is 24.6 electron volt. That's the experimental value. By the way, if you look at this experimental value, then you immediately recognize that this value is essentially deeper than the binding energy of the electron to the proton in the hydrogen atom. So in hydrogen atom, we have the ionization energy equal to 13.6 electron volt. Here we have even deeper bound electron. So if we want to repel an electron, it's not this actually measurement shows you that this is not just a simply bound atom. It's not just sort of an atom that barely exists. It says that this is the atom that exists. It has the deepest actually bound energy as compared to all other atoms in the table, in the Mendeleev table. So I'm just discovering you the number already, and I'm saying in advance that this is the deepest value of the ionization of a single electron out of any atom in the whole table of Mendeleev. So this is a really deeply bound system. Okay, but it's not deeply bound as what we actually got from this crazy model. So this model was oversimplified. Sort of I would say, knew about that, right? That we are going to make a criminal assumption. So this criminal assumption says that we actually found some much more exaggerated values compared to experimentally obtained value. So it's about a factor of 2 out of the story. So it's not surprising. So we have to go to more complex story. So let's go for a more complex considerations. And this next step of doing the consideration in this story is to go to perturbation theory. So let's assume, so this is sort of another criminal assumption, but it is less criminal than the first one, right? So we are going step after the step. So we were real criminals. Here we're sort of improving ourselves. Then we will try to improve ourselves more. And the ultimate improvement that to release you from the prison would be the homework, of course. Okay, so at the homework, you will be able to bring the light into the story and to really calculate the real bound state of the electrons of helium atoms that will release you from the prison. So until submitting this homework, you are from today down to the prison. Those of you who will drop in the middle of this walk, so it's not an easy task, but doable. You will be, living in the prison forever. So I suggest you not to drop in the middle this walk. Anyway, so let's be a bit less criminal than before. So let's consider this interaction as the perturbation theory. So of course, what is the perturbation, right? So the perturbation is that we consider, right, in this story, to calculate this stuff. So we essentially assume the Hamiltonian is the sum of the kinetic energy of the electron plus Coulomb interaction of the electron with the nucleus, plus the kinetic energy of the second electron and the Coulomb interaction of the second electron between the nucleus. So that was sort of twice H0, right? So in this story, we consider the Hamiltonian to be just a symbol of H0 of the hydrogen plus H0 of hydrogen, right? That was essentially the Hamiltonian that we consider here, and that allowed us to calculate easily the binding energy of the electron according to a hydrogen atom. So now that in this story, we remind to ourselves that electrons are charged particles and they can interact with each other. So in this situation, the Hamiltonian will be the H0 Hamiltonian plus H0 Hamiltonian. That's the same as we had before. But now we have to consider the interaction between the two electrons. Here's the atomic units. Therefore, our interaction term does not take into account all this. So there is Z that should be in it. Well, there is no Z, right? So because there are two electrons, so each of them has charge of the electron. So that's the hard part. Okay. So this is the hard part. But now, for now, we actually take this part and consider it according to perturbation theory. So what is the meaning of that? We say that these two parts of the Hamiltonian define the wave functions. So the wave functions stay as the wave function of the hydrogen atom. And now we just take this part as a perturbation to these two Hamiltonians, right? To this main Hamiltonian. And we just calculate it according to first order perturbation theory. So we need to calculate this type of, so the energy shift will be equal just to the wave function, right? Closing over the R1, R2, R1 minus R2. That's the interaction between the electrons. So we have to calculate this term. Okay? That's what we need to do in order to try to apply the perturbation theory. So to calculate this term, we have to use some mathematical tricks. And one of the best one to use is this mathematical identity. So mass identity that I will put on the screen will be useful for all the story that we have here with the with two electron atom. Well, not only with two electron atoms, with many electron atoms, but you know, the story of two electron atoms is very complicated. So the many electron atoms will be hopeless indeed. So we are doing this the following mass identity. So 1 over R1 minus R2 is essentially equal to some expansion into angular into the y functions. So this angular moment functions. It's equal to sum between L equal to 0 to infinity and sum over M between minus L to L, and then it goes like that. So it's 4 pi divided by 2L plus 1 multiplied by spherical harmonic y L M star. So it's a complex conjugate of the spherical harmonic L M multiplied by spherical harmonic L M. That's spherical harmonic of R1 part, which defines the theta 1 and theta 2. Sorry, theta 1 and phi 1, right? So R1 means theta 1, phi 1. Here I have the spherical harmonic of Lm, which acts on R2, which defines phi 2 and theta 2. And then I have the multiplication factor over R small to the power of L divided by R big into the power of L plus 1. R small and R big are essentially, R small is equal to mean between the R1 and R2. So it's either R1 or R2, depending who is the largest guy. And R large essentially, of course, is equal to maximum of the R1 or R2. So that's the mass identity. So this means that I can actually take this term and expand it in spherical harmonics. So it's not something that I'm going to prove you. So this is the math identity. So if you want to prove that, go to math department, go to Google, go to books, see how this math identity got to life. Okay, but this is extremely useful mathematical identity in order to get all sorts of integrals that are related. So this is the integral, which is not a very simple one. And if you use this trick, it becomes simple. If you don't use this trick, it becomes hopeless, right? So that's the math tricks to do, usually do, right? So they make the life either hopeless or useful. So let's try to push forward our criminal story. We are trying to calculate essentially this part of the story. This part requires us essentially to make a certain assumption about the wave function, right? Because if you want to calculate this correction to the energy, so we have to close this energy between the two wave functions. And these wave functions, we have to know what are they. So we assume that this is the correct Hamiltonian, right? And this is the perturbation. So this wave function should be the solution of this Hamiltonian. But we know something about the electrons. So electrons are fermionic particles. So fermionic particles require antisymmetrization of the wave function. So we have to know that the wave function is antisymmetric, right? Because we are dealing here with a wave function of 2 electrons. So 2 electrons has to be, so this wave function has to be antisymmetric with exchange of 2 electrons. So this means that we have to remember that this wave function essentially has 2 parts, right? So the wave function has the part of spatial coordinates and the spin coordinates. So these are 2 parts of the wave function lives on different Hilbert space. Therefore, we can actually use, right, these 2 parts of the wave function in order to construct the wave function to be antisymmetric, while the antisymmetrization should be either there on the spin degrees of freedom or on the spatial degrees of freedom. So we can think about the solution in this situation, that these 2 electrons on the ground state of the hydrogen atom. So this means that we have to take these spatial coordinates to be equal to the ground state of hydrogen atom. So this wave function is just each electron occupy the same orbital, right? But it cannot occupy the same orbital without changing saying about something about the spins. So we can take, in this situation, the wave function that is construct of 2 parts, and say something about the spin part of the story. The spin part of the story should give us antisymmetrization, while the spatial part will give us essentially symmetric. It will be symmetric. So we know that this wave function is the solution of this H0. So it's a ground state hydrogenic wave function. But we also know that the spin part of this wave function should be antisymmetric, right, in order to keep the whole wave function antisymmetric. So we can say that from the spatial point of view, so this wave function now depends on R1 and R2. That's the wave function that we should use in order to calculate this part. But this wave function we can write as separable, right, wave function. So it will be wave function of the ground state depending on R1 of one electron multiplied by the wave function 1, 0, 0 of the second electron, R2. So that's a simple separable wave function, spatial wave function, which certainly is the correct wave function for these two Hamiltonians, H0, which for R1 and H0 for R2, right? So that's the difference between these two. Essentially, I have to write that in order to be completely correct, right? And make less criminal things starting from the beginning, right? I have to take here R1 and have to write here R2. So these two Hamiltonians work on different electrons. So and this wave function satisfies these two Hamiltonians. That's great. This is okay. But this wave function is symmetric. Right? So if this wave function is symmetric, does not answer the antisymmetrization requirement of the wave function of two electrons. And this should come from the part which is the spin part of the wave function, which depend on spins. And then this spin part should be antisymmetric. And we know that it's only two spins, 1/2. So they can be either in the situation of triplet or singlet. So triplet is a symmetric part, so we cannot use here triplet situation of two spins. So we have to take into account that our wave function here is the wave function of the singlet. So up, down, minus, down, up. So then the total wave function, that is the symmetric spatial wave function and antisymmetric spin part of this wave function, will answer this basic requirement that the wave function is antisymmetric. So, but in this situation, the partial part is symmetric, and this is what we need here in this Hamiltonian, because this part does not act on spins. Therefore, spin degree of freedom remains the same. It's antisymmetric. So, therefore, we are going to solve this for this wave function. Okay, so the symmetric wave function. Okay, very good. So this is essentially an important requirement, an important point to remember, that we have to we have to have antisymmetric wave function for two electrons. Okay, now we can calculate essentially this term that we know now, the wave function. So this is now goes like that. So we calculate the delta E here. This should be the integral over the psi 100 squared, 1 divided by R1 minus R2, this part, multiplied by the modulus of 100 squared. So this will be the R1, right, and this will be the R2. So this integral should be the integral that goes over the R1, d3 R1, and d3 R2. That's the integral that we have to take, right? So we will use, of course, the trick that we just introduced. So we will use this trick of the math. So we are going to take this term and develop it into spherical harmonics. So therefore, this integral will be equal to so z to the 6th power So I remind you what are these wave functions, right? So this wave function psi1 of our psi1 0 0 of our theta phi is equal to z divided by a0 to the power of 3/2 multiplied by 2 multiplied by e to the power of minus z divided by a0 Bohr radius. So that's the ground state of the hydrogen wave function multiplied by the spherical harmonic of 0 0, right? So that's the wave function that we are using in order to calculate this integral. And so this, therefore, the development of this part of this integral into spherical harmonics, so it will give us certain coefficients here. So there will be y0 0, which has also pi inside. And we have z to the 6th power divided by pi into 2. Right, so that in the 6th power gives us, because we have one wave function squared, it gives us z to the 3rd power, and the second one gives another z to the 3rd power. Then we have z to the 6th power, and this has come from the spherical harmonics, the pi square that we open. So now part of them we remain in the story, part of them we open. So now it goes like a sum, according to what is required here, from L from 0 to infinity, sum of m that goes from minus L to L, 4 pi squared divided by 2L plus 1, the integral now over R1 from 0 to infinity, R1 squared dr1 times, so I'm going here to write it here, times integral over R2 between 0 and infinity. So it goes to R2 squared dr2 multiply by e to the power minus 2z R1 plus R2 multiply by this part R small to the power of L divided by R large to the power of L plus 1 multiply. This is actually the part that I wrote here. This is the radial part. In addition to the radial part, we have spherical harmonic parts, the part that depend on theta and phi. So that's the additional integral that goes over d theta 1 d phi 1 multiplied by y, spherical harmonic y, complex conjugate, Lm of theta 1 phi 1 multiply by spherical harmonic of 0 0, which comes from the initial wave function 0 0, theta 1 theta phi 1. That's one integral. There is a second integral over theta and phi d theta 2 d phi 2 y spherical harmonics of Lm theta 2 phi 2 complex conjugate multiplied by spherical harmonics of 0 0 theta 1 theta 2 phi 2. That's spherical harmonics that's come from the second integral, so second wave function. So but this wave function was squared, right? So here spherical harmonics should be squared. So here we have only to the first power. So the second spherical harmonics gives us from here and from here gives us this 1 over pi squared. Okay? So this is the monstrous integral that we have to take. the point is that this nonsense integral becomes extremely easy because you have a multiplication of these spherical harmonics here. So this spherical harmonics is 0, 0. And this is sum over all spherical harmonics of L and M, right? So this is a sum of that. But this is the powerful method here, right? Because of these multiplications, the sum drops away, right? So it goes away because of the completeness of spherical harmonic functions, right? So, and orthogonality, sorry, not the completeness, but the orthogonality of wave functions. So this integral is essentially a delta function for L. So it's normalized, right? The spherical harmonic is normalized, so it's a delta function, this delta function. Everything becomes easier because now, because of the monstrous integral, we remains only, the remaining integral is only the radial part of this story. Okay, very good. So now we have here, this story is equal to z to the 6th power divided by pi squared. So now, so we sort of, you know, just to make the story complete, I will write this part still with sum L from 0 to infinity. This goes from M minus L to L. Then I have the integral R1 squared dr1 from 0 to infinity. Then I have the integral over R2 dr2 squared R2 from 0 to infinity. E to the power minus 2z R1 plus R2. Here I have this multiplication of R small to the power of L, R large to the power of L plus 1. But this angular integral will give us the delta function of L0 and delta function of M0. And that's, of course, the easy things, the easy story here, because now essentially this delta function drops away the sum, this delta function drops away in the second sum, and they also pay attention that here we have the ratio between R small to the power of L and R large to the power of L plus 1. So because the L, the only L that gives us contribution into this integral will be equal to 0, so R small to the power of 0 will give us R1, so it drops away. The only thing that we have in this story is R large to the power of 1, because this is L plus 1, right? So it's should be clearly seen here, right? So if we write down what is left from this integral, we have here 16 times of z to the power of 6. Multiplied by integral of this one and that one. So from 0 to infinity R1 squared dr1. The integral from 0 to infinity R2 squared dr2. So multiplied by this exponential factor minus 2z R1 plus R2. And this is multiplied by 1 divided by R large. That's it. That's the integral that we have to calculate. So now we know that R large gives us essentially this gives us essentially the R1 or R2 depending, right, if R1 is larger or R2 is larger. So this means that we have to divide this integral into two parts. First part will be from 0 to R1, and then the second part will be from R1 to infinity. Otherwise, we cannot write correctly this part, right? So let's do that. So then this integral will be equal to 16z to the sixth power. Now the integral over 0 to infinity r1 squared dr1, and now, sorry, yes, right. So, and then now we are getting this minus e to the power of minus 2z r1. And now we have to multiply that or on sum of two contributions. One contribution will give me the integral between 0 to r1 of dr2 r2 squared multiplied by e to the power minus 2z r2. And here we get this contribution of 1 over it's not there. So this part, 1 over r large, here in this situation I'm going from, the r2 is going from 0 to r1, so it's a smaller part. So from here I know that this is 1 divided by r1. And this is not the part of the integration because the integration goes according to r2, so I can get it away from the integral. And now the second part goes from r1 to infinity. So in this situation, the r2 should be here, right? Instead of here, it's either r1 or r2. So in this part of the integration, it's r1. In this part of the integration, it's r2. So it's the part of the integral, r2. And then it's divided by r2. So here, this r2 in the second power goes away. So I have only the one, this is the first power of the r2. And here I have the e to the power minus 2z r2. That's the full integration now, once we take into account this contribution of 1 over r large, right? So which can be either large or small. So now this is equal to, now we can take this integral, so perform this integral. And so yeah, I will not do that, so it's table integrals. So I'll give you the answer. The answer is equal to 5 divided by 8 multiplied by z. So this is essentially the final answer of this integral. So this integral, I remind you, is the calculation of the correction to the energy, right? So I can say you that this is just delta E is equal to now 5 divided by 8 multiplied by z, okay? In atomic units, right? So it should be in atomic units. So that's the contribution of the perturbation theory, right? So this is essentially the calculation of this part. Once we assume the same orbitals and the symmetric wave function for ground state electrons, partial part of this of the wave function. So now that's the answer. So let's see what we get from that story. So for helium atom, Z is equal to 2. This is the atom number. So that this Z equal to 2 means that delta E is equal to 10 times divided by 8, right? So which is the 5 divided by 4 in atomic units. Well, that's the delta E correction. So if we calculate this in each atomic unit, right? So atomic unit is 27. It's twice, 2 times the 13.6 electron volts. This is the atomic unit of energy. So 5/4 of the atomic unit of energy in a real unit will be equal to 34 electron volt. So this calculation gives us the interaction energy between the two electrons equal to 34 electron volts. Okay? So that means that if we now calculate the total energy, so the total energy will be the sum, right? So the E is equal to, so this, you know, I had it here, so I removed it. We had the calculation of two electrons that are equal to minus 109, so 109 electron volts if there is no interaction between the electrons. So in our first criminal way, right, that is removed here, it was too criminal, but it gave a number. So this number essentially should be corrected by not a very small, right? Well, from this point of view, you know, we have to start to question ourselves how good at all the perturbation theory can work in this story, because essentially this perturbation should be compared to the binding energy of two electrons without any interaction between these two electrons, and this is equal to minus 109 electron volts, right? So this means that E, the final, is minus 1. So it's exactly like if you take 13.6 and multiply by 8, you get it 108.8 electron volt plus 34 electron volt that we just calculated right now. So now we have this to be equal to minus 74.8 electron volts. So the measured value, for that's the measured value to extract one electron out of helium atom, but to ionize two electrons, well, so what we calculate here, this is the binding energy of two electrons to the atom. So this value I can add here. So the measured value is minus 79.02 electron volts. So what we calculate now with the use of perturbation theory is this number. So it's off about, say, less than 10%, right? It would be good for other theories, right? So for other elements, so for other part of physics, it would be probably good, right? But not for atomic physics. So it's less criminal than the initial assumption, right? So, but we see that this correction, so the interaction between two electrons, even if we take the calculations due to the perturbation theory, it's not small. It's about 30%. So now, if it's about 30%, we have to ask ourselves, probably our less criminal way is probably less criminal, but still very criminal, because the perturbation theory, which is of the order of 30% of the central result, seems to be questionable. You know, it should be questioned how good it is to use the perturbation theory. So it's not surprising that this calculation is not that exact as compared to what we would, you know, expect to see from the interaction energy. So, but it gives a certain meaningful result. This meaningful result says that the interaction between the two electrons is not small. So it's reasonable. So this is something that we would, I would say, you know, it wouldn't be criminal to think about that from the beginning. So, right, the interaction between two electrons is not small, especially if these two electrons sit on the same orbital. That's essentially the initial. Yeah, right. So that's the initial part of this calculation. It's here, right? We take this wave function to be a multiplication of these two wave functions of the same orbital for two electrons. Okay, so now essentially this result can be calculated a bit differently. So this 34 electron volt can be calculated by some consideration of classical distribution, density of charge density of the electron. So if you take the electron and make it distributed over the sphere of the radius of the order of Bohr radius, and then you try to calculate the interaction energy between two spheres, overlapping spheres, you will essentially get this result. So if you do it correctly, which is essentially what we do. So this is more or less the interaction energy between these two charged spheres with charge density equal to the electronic. So the integral over the charge density gives the electron charge. Okay, now let's do next step, right? Because we know this is not good enough, so let's try to be closer to getting out of the prison. And I'm telling you that this result, that the next result will be the last step that we do together. Then I will almost leave you to your own rights to get out of the prison. But of course, I will tell you the story how to do that, or at least, you know, I'll bring you to some ideas how to do that. Well, I essentially I will write down the integral that you will have to do, which is not a really integral, but the sort of the equation, which is the differential integral equation that you will have to solve in order to get the right orbital. But the next thing that we will do, we will try to solve this story by another method. So, and let's try to say that, you know, what is not good in this approach. So, what is not good in this approach is to assume that the wave function is still the wave function of a hydrogen atom, right? So, this is sort of not a very good assumption because these two electrons still interact between each other. So it's not a very good idea to use exactly the same wave function in order to try to estimate the energy due to the perturbation theory. So this means that essentially we don't know what the wave function. So if you know what the wave function is, we cannot use the perturbation theory. So it's a closing loop. So we have to use a completely different method. So this completely different method called the variational principle. So this is what we are going to do. So the third way out of this story is to use a different method. So it's not something that we used before. Some of you know, some of you don't. If you don't, listen to me. If you know, listen to me. It's more or less the third way to go out. So the third way is the variational principle. The idea is simple. So the idea is means the following. So let's imagine that there is a wave function that we don't know it. So we don't know the wave function, but we know that the true wave function should minimize the energy of the system, right? So that's a reasonable assumption, and that's the assumption of the variational principle. It means let's imagine that we have a wave function with a certain parameter. So we have to guess the wave function in the variational principle. That's the whole point, right? So intelligent guess of the wave function brings you to good result. So now that's the magic trick of this story. So if you know how to write the correct function with a certain variational parameter, then you will be able to get successful results. But you have to have an intelligent guess about how the wave function should look like and to choose a correct parameter in this wave function in order to minimize the energy according to this parameter. So the key point here is to guess correctly the wave function, right? So, and this is of course the the most important most important part in this story. So what we know, so what we say, the variational principle, the basic principle of this variational principle is just to say that there is a certain wave function that we close on Hamiltonian, so expectation value of the Hamiltonian with this wave function divided by the normalized, right, on the wave function. This should be always larger or equal to the true ground state of the system. That's essentially all what this variational principle means. So we have to look for this wave function. So, and now we need to guess about something about this wave function. So this is the key point, guessing walk. So we will guess the following wave function. So it will be ze to the third power divided by pi, normalization the same that we have here, right? So now this is a single wave function. Here we are writing the wave function of R, which depend on R1 and R2, so it's a multiplication of these two functions. So it's giving z to the third power divided by pi due to this due to this spherical harmonics pi arrive. So and now I have, so I consider the wave function with this parameter, right? So which parameter I can choose here? The simplest guesswork. The simplest guesswork that you can walk. So you suggest to change A0, right? So it's almost there, because there is no that much to choose. So if we want to leave this wave function as it is, right? So we have only one parameter to choose, and this parameter is essentially the ratio between z divided by A0. So now the question is, what do you want to change, right? The Bohr radius. I prefer not to touch the Bohr radius, because they're not only me. So usually people prefer not to touch Bohr radius, because Bohr radius is the atomic unit measurement of lengths. So you would prefer not to touch that. But the atomic number z is a good number to sort of play with, because this is just the wave function, and usually if you look at that of this guy, right? You see that you better will change something which sits in upper part of your ratio, right? And then, so what we actually want to change is this z. So instead of taking z equal to 2, this is what prescription of the atom number of helium atom says us to do. So we have to take z equal to 2. We actually take z different. So we allow this z to be different, say some effective number that we want to find, to minimize this energy according to this parameter. Okay? That's the idea. So why this is true? Why actually z will not be equal to 2? So there is a general idea that can tell you that if we keep our atom essentially the same as the hydrogen atom, so with the same orbitals, and we keep them sort of look the same as the familiar hydrogen atoms, we have the same wave functions. But now we have two electrons that orbit the same orbital, and these two electrons can be close or away from the atom, right? And not necessarily the same time. So one electron can be closer and the second can be farther away. So the idea is that, and this is a simple idea that gives you clear understanding of multi-electron atom. So this is a general idea that we will see it when we talk about multi-electron atom. So once the electron is close to the nucleus, so it feels the full charge of the nucleus, and this full charge is equal to 2. That's reasonable. But once the electron goes away from the nucleus, so it occupies some tail of the wave function. Once it's there, so there is a big chance that the second electron actually goes close to the nucleus. This is because the wave function just goes exponentially down, right? So, and if one electron occupies somewhere a tail, well, there is a very little chance that the second electron will occupy the same tail. It will be probably somewhere closer to the nucleus. So in this situation, the second electron that is away from the nucleus, the charge of the nucleus is partially screened by the first electron. And this partial screening gives us the idea that the Z is not the same, should not be the same if you are occupying the different parts of the wave function. So if the wave function is looking like that, right? So this decay, exponential decay of this wave function. So when you close to the position of the nucleus, so you imagine that the Z will be close to 2. So the second electron will not make any screening. But once you are occupying some tail, so the first electron most probably will be actually close because this is the largest probability. And then this tail will see a different Z. So effective Z is not that crazy to think about as a variational parameter for our variational principle. Okay, so after saying that, we are going and doing the following assumptions, so that the Z is the effective Z. So this is why there is E here in this story. So it means that we don't know actually. This is the parameter of our wave function. So, but otherwise, this wave function looks the same. So otherwise, this wave function looks the same. So it looks like minus ZE, effective Z number, multiplied by R1 plus R2. So, and I remind you, it's in atomic units. So, don't sleep. A0 is equal to 1. So I don't have to divide it. So that's in atomic units, right? So now we are getting the following. So we are having this wave function. So now we are taking this wave function and apply again the perturbation theory. So we are going according to perturbation theory, but now the wave function has a certain parameter in it. So we will vary this energy that we get according to this parameter to find the final parameter of the story. So now we have to take this wave function and close the Hamiltonian with this wave function, the new wave function. The Hamiltonian as previous, right? So this Hamiltonian has the two parts, which is equal to two parts which are H0 parts, which depend on coordinates. So Laplacian operator depends on coordinate R1, so the kinetic energy of the first electron, minus half Laplacian of the R2, so the kinetic energy of the second electron, then the interaction energy of first electron with the nucleus, and the interaction energy with the second electron with the nucleus. And here I have Z, not ZE, not the effective atomic number, but the real atomic number, because this is the real interaction. That's H0. So here the real interaction, and Z is equal to 2. Okay, that's the real Z. And now we have the additional part, which is the interaction energy of R1 minus R2 modulus. That should be the expectation value that we have to close with the wave function, which has ZE, effective atomic number in this exponential decay. So now we can calculate the parts. So the calculation of these parts, right, of this R Laplacian squared. So the kinetic energy, still the wave function looks essentially the same as the hydrogenic function, but the only thing different is this ZE. So we don't need to perform all these integrals because we already did that. So, and this is according to variational principle. Remember that there is a relation between the kinetic energy and the potential energy. So we actually calculated the potential energy first and then said what should be the expectation value here, or what the integral here. So it should be equal to 1/2 of ZE squared. In atomic units, we are working in atomic units. We are working in atomic units, Remember that. So now we are going to calculate the second part, which is the potential energy, which is 1/r phi. I'm putting here r because this can be I1 or 2, doesn't matter. They are equal to each other, and they should be equal to ZE. They should be equal to ZE. Okay, good. So now we calculated already the interaction part in the previous calculations with the perturbation theory. So the part of this phi 1 divided by R1 minus R2, these two guys closing with the wave function, the new wave function that we imagine here, this gives me the new value, which we know from here, it's 5 divided by 8 z, right? So it's 5 divided by 8 ze. Fine. So now we can take everything together and write what is the energy here in this story. So all parts of the energy that we calculated. So we have the following expectation value of the whole Hamiltonian. It gives me so it gives me ZE squared so ZE squared minus 2 ZE plus 5 divided by 8 ZE. So Z here is come from this Z. So this expectation value is 1/r, gives us ZE, but it should be multiplied by Z, of course. So I would better probably write it here. It's Z divided by R, that's the potential energy. So I get here ZE. So I have it twice, it's twice. I have twice the kinetic energy. I have it twice. So I have this kinetic energy, this potential energy, and the interaction energy. Right? So that's the energy that I have now. So in order to apply the variational principle, I have to look for the derivative of this energy with respect to ZE, which is equal to 0. That's all what I need to do. Right? So that's the prescription. So d phi h, in order to find the optimal parameter ZE, I have to find this derivative over this parameter equal to 0. So it usually is written as E as a variational, it's the energy which depend on the wave function. So it's a variational principles depend on the wave function. So it's that's essentially is equal to E phi derivative according to the parameter ZE. So this derivative is not complex to take, right? So I will finish it here. So below that line. So it gives us the following. So dE of phi dZe is equal to 2 times ZE minus 2Z plus 5 divided by 8 equal to 0, which means that ZE is equal to some value Z minus 5 divided by 16, which is equal to 1.687 something, right? So 1.6875. So it's less than 2, right? So we get some number. So this is the real Z minus some correction, and this correction gives us something which is less than 2, and this is exactly what we expected according to our, physical reasons, the reasoning of screening. So that's what sounds to be correct. So that's what sounds to be correct, right? So this means that our wave function actually decays faster. Sorry, decays slowly, right? Because this ZE is in the exponential, so instead of decaying with the rate of 2, it decays with the rate of 1.5. So we get wave function a bit larger, right, than the hydrogenic wave function, which is also reasonable because we know that the electrons repel each other. Okay, so that's something that takes together with everything. So now we can, based on this wave function, right, so where we know what is the ZE now, we can essentially calculate the ground state energy, right, and compare it with the experimental results that we what we wrote here, right? So this one and that one. So this also has to be with sign minus. Well, it's the binding energy. So what is this number? So this number is so if you calculate that, so E0 will be equal to minus 77.5 electron volt. Calculating the expectation value. So we can declare victory, right? So it's certainly better than any attempt that we did before. So this method brings us closer to the true result. So the true result is minus 79. Now we are only 2 electron volt away. So 2 electron volt away is about 1% away. So before that we were about 5-6%. Now we cut down the difference between our estimation and the true behavior of the system, right? So at the end we can compare what we calculate with the experimental results. So we don't know how what the electron does around the atom. We can only guess. So our guesswork was not that bad, right? So this guesswork at least brought us to improvement. So here we had the result of 75. Here we got shrink the difference between the real value and calculated value down to 1%. So 1% is a good value. So here, usually, at any branch of physics, you would declare a victory and write the paper. So there are tons of papers written on that, of this variational principle. So why tons of paper? Because this is a guesswork. So if you are intelligent enough, you can come and guess a different wave function. So you can bring more parameters to vary. So here we vary on a single parameter. So it doesn't mean it can be, it should be a single parameter. Bring here 2 parameters and start to vary 2 parameters. You will guess a better wave function, right? So you can guess a different wave function. So if you do a different wave function, this guessing work can bring you to closer to the result. So this I leave to you if you are interested to read tons of papers about that. I'm not going to do that, so I'm just give you the general idea. I'm just saying you that the wave function, to guess the wave function, the correct wave function, can be done better in order to bring the story, but it's still a guesswork. So I will leave this variational principle to those who likes the guessing work, which is a good stuff to do. So I'm not saying that this is not good to solve. You know, it's really gives you the idea what is the difference between the physics and math. You know, if you come to math class and you say that I start from guessing, then you are killed immediately and put into prison without being capable release out of this prison. You will be sentenced to sort of, you know, your lifetime in the prison, right? This is impossible to do when you are talking about the math, but here in physics class we can say that this is not a bad idea to guess what nature does, right? And start to see if we are right and not. And the reason for that, because we have the experimental data. So the experimental data says that what is the true result. Okay, so, but we are not going to do that. So we will do something different. So we'll do a different approach, which is sort of an ultimate approach from this point of view of this course, which called the Hartree-Fock Theory. So we will do that. But before we are doing that, we will do, first of all, the comparison between, so we will try to get some touch on the possible different energy levels of this helium atom. So right to now, we only concentrated on the ground state of helium atom, okay? So ground state of helium atom is okay. But we know that there are different other excited states of the system. And here there was a real question in the beginning of quantum mechanics. So the real question was about the behavior of helium atom that in spectroscopic measurements actually provide two different atoms. So people knew that they work with the helium atom, but there was a two different series of measurements that provided one spectroscopic measurement against the second spectroscopic measurement. They give different series, okay, like a Balmer series, but like a Lehman-Balmer or Paschen, oh, sorry, Paschen, Fund, or and so on and so forth, the names of the series that we discussed for hydrogen atom. In case of helium atoms, there were two distinguished cases. And people call them parahelium and orthohelium, because this was the helium, but it got the two different cases because these two series did not talk to each other, but they were agreed with the general behavior of 1 over n squared. But they sort of provided two different series, and therefore there were two helium atom in the nature. One was parahelium, and the second was orthohelium. And the very great success of early quantum mechanics was to explain this difference. And this is what we are going to do now. So we are going to explain the difference between these two cases. And this is, of course, not two different atoms. This is the same atom. But we will see what is the difference between these two spectroscopic series. Okay, so no questions up to now. We are going to revise everything about that and go to the excited states of a helium atom before we return to the ultimate treatment of any states of helium atom, and not only helium atom, but many electron atoms, which will be the Hartree-Fock theory. So now we are essentially asking ourselves what's going on for the excited state. So we are talking about the excited state of the helium atom. So we are talking about excited state. So excited state means that one electron occupies excited orbital, and the second electron stays on the ground state. So there are different possibilities to have different excitations in helium atom, of course. So we can excite both electrons. We can excite both electrons on the different orbitals. Let us start to use something easy, right? So easy means that we excite only one electron on some orbit, somewhere, NLM orbital. But the one electron stays on the ground state. So that's sort of the easiest assumption regarding the excited state. So, and here we have the two different possibilities. So here in the ground state, the only possibility that we had was essentially to give the antisymmetrization of the wave function to sit in the spin degrees of freedom, because we occupy the same orbital. So we cannot introduce sort of antisymmetrization in the orbital part of the wave function. But once we consider the excited state when one electron is on the excited state and one on the ground state, so they occupy different orbitals. So here, exchange of two electrons can bring us to the situation that we can symmetrize now the spatial wave function, and not only the spin wave function. So now we still have to keep our wave function anti-symmetrized, but we can do that in two different manners. So we can do that one manner. We anti-symmetrize spatial wave function and keep the spin state in symmetrized state, or we took the opposite, right? So therefore, we can actually write the spatial wave function as a superposition of two possibilities, that the first electron sits on the ground state and the second occupy the excited orbital R2, and then we get plus minus of the opposite situation when the first electron occupy the excited orbital LMN R1 multiplied by psi 100 of R2. So this wave function, as you can immediately see, can be either symmetric or antisymmetric, depending on the sign that I choose between the plus, so put here plus or minus. So this spatial wave function can be symmetric or antisymmetric, and it can of course come in, it should come of course, in a combination with the spin part. So if this is symmetric, spin part should be antisymmetric. If this antisymmetric, spin part should be symmetric. Remarkable fact about this specific state. This remarkable fact means that we have now strong correlation between spin and orbit and spatial degrees of freedom. Up until now, there was nothing about that. Okay, but now we have this remarkable correlation between spin degrees of freedom and spatial degrees of freedom, just by fact that we have to symmetrize the wave function, and the wave function is composed of two different parts, spatial and spin part. So if you think about that, it's a deep fact, it's a deep effect that gives rise to some crazy effects in continuation. But the root of these effects is essentially in this introduction of sort of really correlation between spatial degrees of freedom and spin degrees of freedom, which were before completely living on two different parts of Hilbert space. They still live in two different parts of Hilbert space, but they are correlated now. Okay, so now we can get this wave function, right? And now we are sort of can calculate according to perturbation theory what is the energy of this excitation. So it's less crazy to go to perturbation theory in this situation than it was for the ground state. And I hope that you understand why, because in this situation the perturbation theory will be more correct, because the electron, the second electron, is actually going into the excited state, which is farther away from the nucleus, and for its interaction with nucleus will be weaker. So, and the interaction with the second electron will be weaker. So it's sort of more reasonable to think that in this situation perturbation theory will be even more correct than the perturbation theory that we tried to apply for the ground state. Okay, so now that's the wave function that we have to take into account. So calculating without the interaction gives us the energy of 1 and some other principal number. So this is the principal number for one electron. This is the principal number for the second electron. So this gives us without the interaction. So that's the without the interaction. Without the interaction part. So I'm writing here that I know almost for sure that it will be not seen there, but whatever. E to the E1n gives us the minus z squared divided by 2 of the first electron, and then the second electron gives us minus z squared divided by 2n squared, right? So whatever the n is. So it will give us less energy, so the sum of these two parts. That's without the interaction. Now we have to take the interaction part and close this. So to get this interaction part, we have to actually calculate the energy. So now we will have two possibilities, depending on what spatial wave function does. Right? There are two possibilities. There will be either plus or minus. It already hints on the problem that I mentioned before we started to deal with this case. Remember about ortho and parahelium? So here at least I have these two possibilities. So either energy will go with plus or minus wave function. So if I'm taking the wave function of plus or minus, that will close this interaction energy of R1 minus R2. It should be closed with plus minus. Okay, so we have to do that, the integrals. So, but what you need to understand, so essentially we did that already, so because this is combinations for, but we did that for the ground state. Now one of the wave function will be a bit different. So it's still work has to be done. But we can write immediately that there will be two possibilities actually in case of plus or minus. So in case of plus, E plus will give us some integral j plus some integral k, and in case of minus we will have the same integral I minus the same integral k. So there will be two different distinguished cases, one plus one minus, with two contributions. One we call direct integral, contribution of the direct integral, and the second one will be called an exchange integral. So this exchange integral gives rise to the exchange interaction. So that's where this, first time where the exchange interaction was essentially realized to exist. This exchange interactions, of course, has very large consequences for solid-state physics. But now we are dealing with the electrons in helium atom. So the exchange, the direct integral. So we have two integrals: direct integral, direct integral. So this direct integral gives us j, so we can write it like j is equal to the integral over the phase function psi 0, 0, psi 1, 0, 0 of the R1 squared, 1 divided by R1 minus R2, multiplied by psi n Lm of the second electron squared. This should be taking over d3r1, d3r2. That's the direct integral. So we have the probability to find the first integral, the first electron on the first orbital, and the second electron on the excited orbital. That's the direct integral. This is something that we should we sort of would expect to have, right? So that this direct integral is sort of expected. What is less expected is this exchange integral. So this exchange integral is equal to the possibility to find, you know, this mixture of 1, 0, 0 complex conjugate to be R1, psi NLM complex conjugate to be R2, 1 over R1 minus R2. And here I have psi 1, 0, 0. Sorry for that. Sorry, psi 1, 0, 0 of R2 to find the second atom on, so second electron on the orbital 1, 0, 0, and the first electron on the orbital R1. And this should be D3R1, D3R2. That's, this is an important part which has no classical analogy whatsoever you will try to find. So this one has the classical analogy. That's exactly the same interaction that we calculated before for the ground state. This is the interaction between the density distribution of the charge of one electron as compared to the second electron. So this is the density distribution, charge distribution of the first electron, this charge distribution of density, charge density, density of charge, charge of density, density of charge, charge of the electron distributed in a certain density, right? So density distribution of this electron, density distribution of the second electron, and that's what the first direct integral gives you, right? So that's the same thing that we calculated before. This guy has a completely different story. So it has a probability to find the first electron on the orbital 1, 0, 0 and the second electron on the same orbital, right? So it's a mixture, it's exchange term. So that's the cold exchange integral. It's exchange term. This is exchange interaction. This exchange interaction comes due to the fact that we can exchange between the two electrons. The only reason this term exists is because we can exchange between the position of the electron. They are indistinguishable particles. We can put one on the orbitals 1, 0, 0, or the second one on 1, 0, 0. And that's the only reason this term exists. There's no anyone that can find something similar in the classical treatment whatsoever. So it just cannot exist. And it cannot exist because we are dealing with wave function and not the density. Because the density comes from the wave function squared, right? So, but here we can, the wave function, exchange between them from one side and the second side. That's very important to understand. This is exchange interaction is a purely quantum mechanical effect. No any classical analogy to that you can imagine. Okay, so now one have to calculate them, this story. So I'm not going to calculate again these integrals, so we did that already, but I will do that. So I will just write down sort of what to do, right? What need to be done in order to calculate that. Okay. So so this is the excited state, so it's not second, it's the excited state. So this excited state has to be calculated based on wave function Lmn of the position R. So suppose that we are dealing with some n orbital n Lm. This Rnl as a function of R, and this is y Lm of the function of theta and phi. That's as usual. So some orbital. So now this J direct integral Jnal will be the integral over the R dr2 R2 squared multiplied by Rnl squared R2. So you have to go and see what orbital you occupy in order to know how this wave function looks like. Then you go from 0 to infinity, and then R1 squared multiplied by R10 squared 1 over R large, right? So that's the direct integral. So this direct integral is essentially the same as we saw for ground state energy. The difference is that here you take a different orbital. If you go to a ground state orbital, you will have here ground, so exactly the same integral that we calculated before. So now the exchange integral has some more funny results. So Knvl is equal to 1 divided by 2L plus 1, the integral between 0 and infinity, dr2 R2 squared, R10 R2 multiplied by Rnl of the R2, integral over 0 to infinity, dr1 multiplied by R1 squared, R10 R1 multiplied by Rnl R1 R is small to the power of L divided by R large to the power of L plus 1. So taking this integral requires a little bit work. This one we already did, this one we didn't, but it's essentially the same sort of procedure of taking care carefully about these guys. Sorry. So you have already something in the in the upper part of your ratio. This will be the exchange integral. It's not 0. No, okay, it's not 0. And this exchange, therefore the energy that we are actually getting out of the story, so without exactly calculating, because in order to exactly calculate now something, we have to take a certain orbital, right? Or we can take this general wave function that will give us some quite complex expressions of these integrals. But it's doable, you know, especially if you choose certain orbital. And then, therefore, we actually get, you know, if we are sitting at certain energy level, so this energy level, right, describes this excitation of, so this excitation wave function of this wave function, corresponds to this wave function. So this energy level is actually splits into two. So it splits in one energy level and the second energy level. So this one energy level gives us corresponds to psi plus, which has higher energy level according to what we know here. So it's E plus, it's the direct integral plus exchange integral. So it gives us psi plus, and this gives us psi minus. Right, so there are two possibilities now. The energy level, the excited energy level is split now into two energy levels. One corresponds to symmetric wave function, one spatial wave function. So one corresponds to a antisymmetric wave function, spatial wave function. So now this, as we saw before, once we have to remember that our wave function, total wave function, has to be antisymmetrized. So if we have symmetric spatial wave function, it has to be complemented with the spin wave function, which is antisymmetric. This spin wave function has to be antisymmetric in order to keep the total wave function antisymmetric. So in this wave function, this spatial wave function is already antisymmetric. So if this spatial wave function antisymmetric, I have to fill it with the spatial wave function with the spin wave function, which is symmetric. So that's the correlation between these two degrees of freedom, the spin degrees of freedom and the spatial degrees of freedom. So now it means that if we have this energy level, so the spin will be symmetric. So symmetric spin means the triplet state. That's triplet. That's triplet. So, and it has three possibilities, right? So up, up, down, plus down, up. That's the triplet state, and this is the singlet state. That's a singlet. This corresponds to singlet. This corresponds to triplet. So singlet, and you see that the singlet state in energy higher than the triplet state. Okay, so triplet state is lower in energy than the singlet state. So why is that? So we can actually find some reasonable explanation for that. So there is some reason that you can think about that intuitively. So once we are talking about triplet state, the triplet spin state requires different orbitals. So the spins actually, avoid each other. So they cannot sit on the same position because they have the same spin state. Right? The Pauli principle says that this wave function has to be antisymmetric. So this means that actually electrons have the same sort of spin, right? So the spin up, up, or down, down, or plus down, up, plus down, up. Anyway, in any case, they have the same spin. They cannot occupy the same position in space due to the Pauli principle. They avoid each other, and due to the avoiding each other, their interaction energy is smaller. They already, due to the Pauli principle, avoid each other, so they cannot sit on the same position in the space. So if not sitting in the same, and you know that the interaction between them goes like a 1 over r, if they are away from each other due to the Pauli exclusion principle, they interact less than those who sits in the singlet state. Singlet state is down up minus up down, and this means that they are in a different spin state, so they can be at the same position in space, right? So this is a symmetric situation of space as the previous orbital, that they occupied exactly the same orbital, so they can sit in the same position in space, so they interact more than those that interact in the triplet state, and that's the reason they are higher in energy. So you can see some reasonable, so see that, you know, it's quite amazing, I would say. So because we had no essentially spin in the story, right? So we didn't took any care of the spin, so we didn't calculate anything for the spin wave function on the angular degrees of freedom. We only calculated spatial degrees of freedom, but we actually ended up with a strong correlation between the spatial degrees of freedom and spin degrees of freedom. So we saw already them, they should exist, and we see them exist, but now it's really translated into the you know, the appearance of strong correlation between the spin degrees of freedom and the spatial degrees of freedom. This strong correlation is the core of the quantum physics, right? The quantum many-body physics is the core of this, all this trying to triplet or to understand how this strong correlation behaves. This strong correlation appears from nowhere, So just from requirement to symmetrize the wave function, this is what it's come from. Right, so and it's this requirement of anti-symmetrization of the wave function of the Pauli principle ended up in building a strongly correlated wave function, which gives us a strong correlation between spatial degrees of freedom and spin degrees of freedom. This is purely quantum effect, and you can see it on as simple situation as helium atom, right? So we don't need a very strong and very complex environment of solid state physics. And this is the explanation of two different spectroscopy lines in a helium atom. So one is ortho, one is parahelium, but this is the difference between the triplet state and the singlet state. So it's just the different excitation energy levels of helium. One connects singlet states, the second one connects triplet states. So this explanation gives, was essentially the most dramatic success of quantum theory, of an early age of quantum theory in the 30s. The quantum theory were able to explain two different helium atoms that people did not understand how it can be different in a spectroscopic system. So quantum theory were able to understand that, and this was based on purely quantum effect. It was on exchange interactions, which had no any sort of possibility to find in any sort of classical, semi-classical, half-classical, anything to do with classical would not be allowed to do that. You have to introduce the wave function in order to build this state. So it's interesting that essentially, there is no interaction between spins here in this, right, in this sort of. So the only thing that we considered here was spatial degrees of freedom. So the interaction between spins are not here. Not in this story. But because of the strong correlation between spatial degrees of freedom and spin degrees of freedom, we can actually build an effective Hamiltonian that will describe the interaction between spins. Okay? So we can actually capture this behavior by just introducing a certain type of the Hamiltonian, which will introduce the interaction, the real interaction between these two spins. And this will capture the same behavior that we measured here. So for those of you who deals with solid state physics knows that this model usually is the model that people introduced in order to deal with interactions between spins, spin-spin interaction. And these interactions between spins gives us ferromagnetic and paramagnetic order. And this ordering comes out as an interaction between the spins. So essentially, we get the same situation here. So we can describe the situation by effective spin-spin interaction Hamiltonian. We will get the same results, splitting between singlet and triplet states energies. But we get it out just because we keep this crazy situation on the way, accurately taking into account that two electrons can be exchanged between each other because they are indistinguishable particles. So I think that I will stop here. So for today, we will make the more general theory of many electron atom next week. So we will write down this Hartree-Fock theory in order for you to be able to finalize the job and to get the certificate that you are released from the prison. Now I'm putting today in the evening the problem set for the next week, for the next 3 weeks. So you will have a little bit of, larger exercises than the previous one. So anyway, so this means that instead of 5 exercises, set of exercises, we are reducing to 4. So it's not that dramatic. But this is what you will have. Okay, so that's it for today.